In this video, I want to talk about recursion. This might be a topic that you have seen before, but we're going to use this idea quite a lot going forward, so it's a good idea to refresh what's going on here. Anyway, let's say we have a sequence, R1, R2, R3, whatever. We'll call it recursively defined if, as long as n is big enough, so not counting the first few terms, Rn depends on at least one value of the terms that come before it. So Rn depends and is defined by some relation on R1, R2, up to Rn minus 1. And that might not include all of them, but it'll include at least one. And the terms that aren't sufficiently large, the ones that kind of where the recursion relation doesn't hold, we call the initial conditions. So they're the ones that you have to just tell what they are before you can do the recursion. And the equation that relates Rn to the lower terms, we call that the recursion relation. So we'll look at a couple of examples here. The classic is, of course, the Fibonacci sequence. So our initial terms are f0 and f1. Note here that I'm starting at 0 instead of 1 as it was defined in the definition for recursion. Hopefully that's fine. You can kind of start at whatever index you like. So here's our initial terms, f0 and f1. They're our initial terms. And our recursion relation is given by this. And that is the next term in the sequence is the sum of the previous two before it. Fn equals fn minus 1 plus fn minus 2. And I tell you here that this only applies when n is 2 or greater. If n is less than 2, if it's 0 or 1, then they are the initial conditions here. And this is, of course, called the Fibonacci sequence. We can calculate a couple of these things. So we have f0 and f1. f2 is going to be f0 plus f1. So that's 1 plus 1, which is indeed 2. So we know f2 is 2. Do f3 is f2 plus f1, so that's 2 plus 1, which is 3, and f4 is f3 plus f2, which is 3 plus 2, which is 5. Maybe we'll do just one more. f5 is f4 plus f3, so that's 5 plus 3, which is indeed 8. And we'll study some properties of the Fibonacci sequence in this course as well. In fact, we're developing tools as we go that will help us determine some nice things about this. One of the main problems in studying recursions is that if you want to work out the nth term in a recursion sequence, you'll probably have to work out the terms before it if it's recursively defined. Like the Fibonacci sequence, if you wanted to work out, say, f10, you would need f9 plus f8, but to get f9, you'd need f8 plus f7, etc. And that, you can imagine, especially for large terms, is very laborious, and it's not something that we want to do. So a common thing to do is to look for some non-recursive formula for terms in a sequence. So something that doesn't involve previous terms. Just something where you can plug in n or something like that, and it gives you the term in the sequence. And of course, that will allow us to avoid a lot of calculation of lower terms in order to get the term that we're interested in. So we'll do a little example to kind of show what I mean here. So let's say we have our initial terms, a0, a1, and a2. So a0 is 1, a1 is 2, a2 is 4. And a recursion relation is a 3-step one. So an is the sum of an minus 1, an minus 2, and 2 times an minus 3 for any term a3 or greater in index. So when n is greater than or equal to 3. So eventually we'll come up with ways of solving for non-recursive formulas using something called generating functions. But for now, it's not a bad idea to just work out a few terms, and maybe we could take a guess at what a non-recursive formula for this recursion relation is. And so once we guess that formula, we're going to have to prove that it's true. So I think it's a good idea right now for you guys to pause the video, see if you can work out a 3, a 4, a 5, maybe even a 6, a 7. See if you can notice a pattern for what's going on here, and maybe you can come up with a guess for a non-recursive formula for an. So something that doesn't involve calculating the previous terms. You can just some sort of function. So pause the video and try it now. Okay, now that we're back, well, let's use our recursion relation, which I'll write here. It was an equals an minus 1 plus an minus 2 plus 2 copies of an minus 3. Okay, so a3 is going to be a2, which is 4, plus a1, which is 2, plus 2 copies of a0, so 2 times 1, and 4 plus 2 is 8. So a3 is 8. a4 is going to be a3 plus a2 plus 2 copies of a1, so that's 8 plus 4, which is 16. And a5 is going to be a4 plus a3 plus 2 copies of a2, so that's 16 plus 8 is 32. So just from this exploration, you could probably see a good guess for a formula for an. It looks here that we're just doubling every time. So 1 times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So it looks like we indeed have that an is 2 to the n. So that's our guess. But we still have to prove this. Just because we notice the pattern doesn't mean that this pattern always holds. We have to make sure that this is indeed the correct pattern for the recursion relation. So let's do this by strong induction. So we have a 3-step recursion here. So we're going to need 3 base cases in some sense in order to use this recursion. So let's go ahead and make our 3 base cases. So let's go ahead and do that. So let's check. A0 is 1, which is indeed 2 to the 0. That's good. A1 is 2, which is indeed 2 to the 1. That's good. And A2 is 4, which is 2 squared. So that's good. So we have our base case completed. Now, let's do our inductive case. So remember, we're doing strong induction here, so we're going to assume that our relation holds for some value k and all values below that. So we're going to assume that ai equals 2 to the I for all I less than or equal to, let's say, k for some k. So we're going to say this holds for a k minus 1, a k minus 2, and below. And we want to show that a k plus 1 is indeed 2 to the k plus 1. So the next biggest one that isn't covered by our strong induction. Okay, and this one isn't too bad. We're just going to use our recursion relation, and the inductive hypothesis should fall right out. So let's go ahead, let's consider a k plus 1. Well, by the recursion relation, we know that's a k plus a k minus 1 plus 2 copies of a k minus 2. Let's say that's by the recursion relation. And note that all of these guys here fall under our inductive hypothesis. So we can use that. So let's go ahead and use our inductive hypothesis right here. So using our inductive hypothesis, since all of these guys are k or less, we're assuming that that's going to be 2 to the k plus 2 to the k minus 1 plus 2 times 2 to the k minus 2. And you can see what's going to happen here immediately, I think. So here we have k minus 2 2's and an additional 2. So this is 2 to the k plus 2 to the k minus 1, plus this ends up being k minus 1 2's. And then here, similar thing happens. Here we have 2 to the k minus 1, so I can rewrite this as 2 to the k plus 2 times 2 to the k minus 1, which is indeed 2 to the k. So here's k minus 1 2's, here's an additional 2, so that is 2 to the k, so we have k2's. And then similarly, I'll leave kind of that extra step not written, but this is the same thing you can check as 2 to the k plus 1. So we've shown our result by induction. We've shown that our guess for a non-recursive formula for a term in our sequence is correct given the recursion relation and the initial conditions. Okay, so here's a nice one. We want to show that every third Fibonacci number is even. And honestly, there's a couple of ways of doing this. You don't need to use induction to do this. You could probably use a parity argument as well, but induction's a nice, easy way of showing this. So first, let's explore. So we know F0 is 1, F1 is 1, F2 is 2, and that is even. F3 is 3, F4 is 5, F5 is 8, and that's even. F6 is 13, F7 is 21, F8 is 34, and maybe let's do 3 more. F9 is 55, F10 is 89, and F11 is 144. So you can see that indeed every third even number, or every third number, is even starting at F2. So let's write this mathematically what we want to show. So we want to show the index 2, 5, 8, so they go up by 3's here. So it's some multiple of 3 plus 2. So we want to show is that f of 3k plus 2, or maybe we'll say 3n plus 2, because I usually use k in my induction step. 3n plus 2 is even for, and let's say n in the natural numbers with 0. So 0, 1, 2, 3, 4, 5, all the way up. So f2 when n is 0, f5 when n is 1, etc. So we'll do this via induction, of course. So our base case is when n equals 0, so just f2 is indeed 2, we know that, and that's even. That's not too bad. So let's do our inductive case now. So we're going to assume that f of 3k plus 2 is even for some natural number with 0k. And we want to show that f of 3k plus 1 plus 2, which is the same thing as f 3k plus 5, is even. So that's our goal there. So remember, we do have a recursion relation for the Fibonacci number, so we can just use that. So let's consider f of 3k plus 5. So we'll use the recursion relation, and this is the same thing as f of 3k plus 4 plus f of 3k plus 3. And my thought is we need to get a 3k plus 2 term in here so I can use my inductive hypothesis. So we could try using the recursion relation once more, and it makes sense to try it on the larger one. And I'll tell you why my thought process says that. If we did it on the smaller one, I would get 3k plus 2 and 3k plus 1, and that's a little smaller than what I'm looking for here. And then to deal with that 3k plus 2 term, or 3k plus 1 term, I might have to do a bunch of other recursion relations. It might get quite messy. Maybe it would work, but maybe it'd get pretty messy. So my thought is if I do it in this one, then I'll have a 3k plus 3 and a 3k plus 2, and then I have a nice kind of tighter range here, and maybe some things will combine together. So let's do the recursion relation again on this f of 3k plus 4. And I'll put it in brackets just to say we're doing it. So f of 3k plus 4, that's the sum of the previous two terms, so that's f of 3k plus 3 plus f of 3k plus 2. And then we have this f of 3k plus 3 left over, and that's by the recursion relation again. Now, our inductive hypothesis says that this guy is even. That's great. And then can you see right now how we're done, how we've shown that f of 3k plus 5 is indeed even? Well, if we combine like terms, we have 2 copies of f of 3k plus 3. So 2 times f of 3k plus 3 is an even number. So we have an even number plus this even number. So we're going to get another even number. So let's write that down. So this is the same thing as 2 f 3k plus 3s plus f of 3k plus 2. We'll scroll down here. And I'll write this a little informally, but that's fine. So we can say this is basically an even number here. Since it's 2 times something, of course it's even. That's the definition of even. And then this guy here is an even number. Maybe right here, in fact, this is by definition of even. And this guy here is even by the inductive hypothesis. We assumed that f of f 3k plus 2 was even. So we have an even number plus an even number is, of course, an even number. So we're done. We've shown that every third term in the Fibonacci sequence is indeed even.